Right, I guess we can get started. This is the fourth session for this summer's Summer of Data seminar, and we're very lucky to have Furong Huang here. She's an associate professor at UMD. She was in the Bay Area, and we opportunistically got excited to come here and give us a talk about some of her work. She's been doing a lot of very relevant work, things that we've been talking about on Slack channels, including test time reasoning control, world models, and physical intelligence. And today she's going to be talking about building self-improving foundation models. So very excited for you to give a talk. Yeah,
It's really a pleasure to be here, and thank you so much for having me. I had a lot of great conversations today, and I think a lot of the things that you do are very much I'm resonating with. So I'm really excited. Well, so today I'm going to talk about building self-improving foundation models, but specifically I'm going to talk about auditing, actuating, intervention, and finally how to amplify and get this positive reinforced for self-improvement. So starting with foundation models, I'm going to just say, hey, foundation. Everybody think foundation models doing some kind of prediction, or maybe this is too narrow. But if you think about prediction as a more wider concept, then it includes a lot of things like caption generation, explaining, or at the end of the day, it's some kind of generation for predicting. Now, a lot of people think that in order to have a trustworthy foundation model, not only you wanted to just get the output of prediction, but you also wanted to get the reasoning traces. And I think that is no longer a dispute. Everybody would say, yes, I agree. Before, we always think, oh, is this the final prediction correct, right? That is the basic principle for you to judge what's right, what's wrong, what's the, whether the model is good or not. But I think after this, a lot of people have been shifting the mentality to, is the reasoning trace actually safe and grounded or calibrated, or even can it be recoverable or self-correcting, right? I think that's actually the major thing here that we believe static trust really breaks. We wanted to have a more dynamic mindset for doing things. And some examples of, show you a lot of us are talking about hallucination. I'm sure a lot of the hallucination you've seen, like object, action, attribute, whatever, relationship, many different kinds of hallucination out there. But recently we realized there is a lot of perception capabilities that you have to improve on, but also just the fundamentally how you train these models, that you're using a pre-trained large language model and then hook up some kind of visual encoder on top of it. It's actually, just inevitably making sure that the model is relying too much on text prior rather than the visual evidence. And that actually becomes one of the major reasons why we have this kind of hallucination, especially the multi-model language models. Right. So also recently, I think this is not news to you guys anymore. Like a reasoning model may become better at reasoning, but unfortunately it could be less safe. If you think about a jailbreak task where, a normal language model may say, hey, this is bad question, I refuse. But reasoning model actually in the process of trying to think may actually got manipulated or, tricked. And then people are trying different things like, maybe you could say, hey, just think about safety first. And that essentially also didn't really quite work. So what we're thinking is, though, rather than having this, reasoning capabilities is not enough, right? We also wanted some other things. Also, it should not be just a bigger backbone alone. Maybe a bigger backbone would solve some of the problems at some point. But I feel, these are complementary questions where you could even make a model much more stronger, a bigger model much more stronger if you are able to do things better. Right. So one of the things I care about is auditor. Right. So it's auditing or understanding what are the errors, what are the risks, and what are the uncertainties, and then potentially, build critic models or reward models that are able to detect these failure cases. And then also, you wanted to recover, wanted to actually intervene, hopefully early during the reasoning stages, through some kind of test time control methods, such as control decoding, early steering, or step value search, and so on. And this kind of intervention is really, really useful And you could potentially apply it to any size models eventually. And then more than that, right, I'm very excited about self-improvement concept of like, if you are able to do auditing good, and if you are able to do intervention good, then can you amplify that into like, use that as a feedback loop and sort of turn the failures into self-improvement? Is it possible? And so we're going to talk a little bit about that as well today. So finally, you're hoping that your trustworthy output is not only just safe, but it's also more capable and more grounded and being able to do things just overall better, potentially, getting you long horizon agents or lifelong kind of improvement. So overall, it's a system. So with this system, we're thinking, let's talk about the auditing, right? So how do we make auditing better? So what makes a good auditor? Let's think about it for VLMs for a second, because that is something that could be applied to a lot of domains. Now, think about a critic model. If I am able to train a critic model, and I'm not saying that this critic model necessarily has to be anything, could be a language model by itself, or could be some other things. So we could say, hey, how good is this response using this critic model? And hopefully, this critic model could provide a reward signal that later on you can use even for non-verifiable tasks, right? For example, in this very complicated pictures, we are seeing like a lot of like interesting things that you see on the wall. There is like, especially one thing you might find interesting is this thing here, like, is it true or false? Right? It's hard to say. Anyways, so a reward model or a critic model hopefully is able to rate your caption and give you a signal, reward signal later on for you to do further things. Now, also, hopefully the reward model can explain. It can tell you what is wrong and why, and essentially give you a concrete recipe for the model to improve. And then finally, you are hoping that this critic model could also guide you so that you know which response or step we should choose next if you are to generate a lot of candidates, right? So they can choose the best one at potentially even inference time. And of course, this inference time selection could later on, you could just collect that data and fit it back to your model training and then do improvement again. Now, so unfortunately, current VLMs really struggle directly serving as critic models, as you can see here. So we're thinking, what makes a good critic in VLMs, right? So of course, you wanted to have detailed reasoning so that the detailed reasoning will tell you exactly why you come up with a score and why is that a reasonable score. And the first one, that is a generative critic model, is actually Lava Critic. Came out 2025, actually, earlier than that, 2024, I'd say. It got accepted to the BPI 2025, and it's the first one that is using explicit reasoning. So you can see that this is how Lava Critic work, and before coming up with a final score, they have a really good reasoning traces that justifies their score. So this sounds good. One of the things you're thinking, like, although it improved the critic accuracy, it loses general policy capability due to knowledge distillation, unfortunately. And then back then people are thinking, maybe this means that your critic model and policy should be just different, right? So once you train a language model that was able to do general policy tasks so well, somehow all of a sudden it becomes only good at critic and really bad at all these other general tasks. So we're thinking maybe, this just means that there's this intrinsically conflicting thing. Is that really true, right? So I wanted to ask a question of like, can we actually enable strong self-critic without actually separating the critic from the policy? In my opinion, this exploration is kind of important for me to understand whether self-critic could really happen. Now, of course, we're going to use RL here. And the reason why we're using RL is really, we believe that, some papers have shown evidence that RL is the key to break the ceiling. So SFT really memorizes and RL could really generalize. So motivated from that, we did some really, really simple thing. Here is what we did. Critic data reformulation. So, before, a lot of people do like this critic training using SFT, which is essentially, given the image and question, two responses, some evaluation criteria and reason from other strong models, and maybe, also from human possibly, and the preference. Now, so what your SFT does is to mimic how to reason for judgment. But is that really what you should be doing? A very simple critic data reformulation actually changed the whole message. So imagine that you could just take the original kind of SFT data, but rather than using the evaluation criteria and the reason, you just get rid of it. And then in the RL critic training, you're forcing the model, the critic model training, to self-derive the reasoning for judgment. So you're only using the preference. All the judgment has to be self-generated. So that is the simple change here. Sounds really trivial, but this is what we're getting. So training data, you go fed to the model roll out to complete the prediction and then make the final prediction of the action. And in the process, you're really enforced to do a think and then answer kind of response pattern. And then finally, whether the model correctly predict the preference or not, because now you do have the preference as the ground truth, then this becomes a verifiable reward. Although it's an open-ended task, but because you have the preference, you are actually making this into a verifiable reward, which is pretty neat here. So at the end of the day, you can see this so-called the Lava Critic R1 has a pretty impressive improvement in terms of critic capability. Actually, I think this is pretty interesting. It means that this critic training is pretty useful. But also, what's more exciting is that it also doesn't really see much performance drop as a strong policy model itself. So this basically kind of flipped the story, right? When Llama Critic came, people think, oh, maybe policy and critic are just two things. But now this paper shows that if you do things right, they could be one thing, they could be unified. In fact, we also show that if you improve the critic capability, a general reasoning capability could also be improved, which I think is very interesting. So we're doing auditing, we're learning world models. We're learning reward models, but the reward models or these auditors themselves sometimes also need to be audited because they may also make mistakes.
Can I ask?
Yeah.
So in the previous plot, when you have these critic policy getting better, does the policy model itself start self-critiquing in some of the rollouts or not really? It's just a better policy model.
Yeah, so in fact, I think the reasoning trajectory is whatever, no supervision, but there are some kind of self-critique behaviors that just emerged because you're forced to make that preference learning.
Got it.
Yeah, so in some sense, I think this is it's not self-critique, but it's more about reasoning about which action I should be taking, right? Because the critic training was basically giving two actions and choose the one that's preferred. Yeah. So going back to this, reward models are useful, especially when you're trying to do some kind of RL training. But the problem everybody is bothered by is reward models have reward hacking problems. Essentially, they have failures. And how do you discover those failures? In my opinion, is one of the most important questions we should ask for answer the question of whether self-improvement is possible, right? So basically, you don't want it to wait until you're done with your RL training to figure out this thing is wrong. You want it to figure out before you do RL, before you pour all the resources, before you actually train using your rewards, you wanted to figure out what may be wrong with the reward model you're actually trying to steer to or align to. So here is a very simple concept of what we did. Let's say you have preferred responses and non-preferred responses. The preferred ones are triangles and non-preferred ones are circles. And of course, if you learn a good decision boundary based on whatever data you've already collected, this is what you're getting, right? A decision boundary separating from the triangle to the red, triangle to the circle. However, what really happens is you may have these kind of false positive and false negatives. So take a look at the triangle red one. See, it is classified as a low reward, but in fact, it is actually a preferred response. So this is a false negative. And in fact, on the blue dots down there, they are the false positive. They're classified as high reward, but they are actually non-preferred. So the whole reason why we have reward hacking is because we have all these false positive and false negatives that's there that we haven't found yet. And then the question is, how do we actually find them? If we're able to find them, then if we're able to find them, then we are able to just adjust our decision boundaries so that we are making the right decision. The reward models will be improved. So now the real question is, how do I really find them? I choose to use a aligned language model. So if I have an aligned language model, what I can do is, I can test this use this aligned language model to generate tokens. And because it's an aligned language model, the top K tokens are very likely to be aligned. This is a very safe model to start with. So very likely I could trust the top K tokens to be really preferred response if I cared about safety here. Now, what if we search in this top K space and find a token such that the reward is somehow really, really low? And if we're able to find such a token there, then that means, although it's a safe response that I prefer, right? But it's actually classified by my current reward as a low reward token. That's really bad. And what I need to do is to, take this false negative and put it back into my training data set for my reward and refine my reward model. So that's the concept. It's a very simple concept. At the end of the day, you could do this for false negatives. You could also do this for false positives, right? Using a misaligned language model, get the top K, and then find the reward maximal token, right? Same thing you could do. And essentially what we see is a very impressive improvement of 35-45% average robustness improvement. But the good thing about it is you do not have to compromise your reward quality. You are trying to make it more robust, but in terms of in distribution reward quality, it is still very, very high. So now going back to this idea here that I think the self-improving critic potentially, could be really a good recipe for self-improvement, because if you're able to train your model better, if you're able to, train your reward model to be better, you can use that reward model to RL your policy again, and your policy is going to be better. And now with that better policy, you could again use that policy for this controlled decoding to find the blind spot of that reward model here, right? So this is a self-reinforced, right? You could potentially iterate between these alternating steps and then finally get an improvement overall. Okay, so that is this part. Now, I want to move on a little bit to the intervention part. Now I found all the problems in my model, all the errors and mistakes and risks. Can I actually intervene? And more importantly, you wanted to intervene during early reasoning steps. You do not want to wait until everything is already generated. You want to, make sure you do an early steering to make things right at the beginning, so you're not wasting a lot of your compute. Well, once we score a trajectory, can we steer it before it fails? And basically, you're hoping that to transform the critic from post hoc feedback into some kind of step level signal or even second level signal as small resolution as possible, fine resolution as possible. So what is the steering problem? Well, if you formulate the problem here, you hopefully start with a reward model. Basically is your criteria. And of course, there is the question of how do you actually learn the reward model? Nowadays we're all using human feedback, preference, and then learn the reward based on the preference. But let's assume that we have such a model to start with, and we can talk about the practicality of this later on. you want to steer your language model to this reward model. The reason why I put a rho and pi here is rho is trajectory level and pi is token level. They're the same thing. Now, what you need to do is to solve this argmax problem, where based on the current state, which is your context window, you wanted to make sure that your decoded language model or the steered language model is still close to the SFT, original model, not too far away, but also it is steered to the reward specifically. And in fact, this Q star is related to the reward because it's an optimal policy evaluation. I can give you more detailed result about it. But at the end of the day, this steered model should just be something like this, where you have the SFT model multiplied with the exponential of some Q functions that's derived from that reward model. So pictorially, if you take a log scale, what you are doing here is that your steered model could essentially be just the base model plus in log scale, right? Plus some reward function. This reward function is essentially this Q star, which is a trajectory reward under optimal policy. What this means is that you're gonna do like a full generation of the response, and then there's a reward model. Assuming that the full generation is coming from an optimal policy, the reward model can just evaluate it and give you a result, a feedback. And that's the reward we're getting here. So you can steer your language model just based on that reward. Now with this, we really wanted to do steering as early as possible. You don't want to wait until you have the trajectory, right? Because language models are next token predictors. You wanted to make sure that every token generation is steered towards your reward. Well, how do you do that? Well, you could do this, right? Unfortunately, there is a discrepancy if you do this, because what you need for next token steering is actually a reward model kind of granularity for you to steer. But what we have so far, all the reward models are outcome reward models. They only are trained to score the entire trajectory rather than every token. And that creates a discrepancy. As a result, people are trying still to do this, right? So, prior work was just, scoring the partial response, although the reward model is really designed not for that. But if you do it right, our recent work on transfer QSAR and another work, DEAL, was trying to do it right by actually doing the full completion. But this thing, although it's right, you imagine that you have to do this full completion for every token generation. This could be really, really expensive, right? So although it's correct, it's just too slow. In fact, it requires generating full response for every next token sampling. Now, in fact, with my academic setting was like A6000 GPUs or something, like generating such a response of like 500 tokens, it requires you 14 hours. It's just insane, right? So you're doing it right, but you cannot really do it this way. So we reduced it, using a specific work called autoregressive reward model. We're trained a next token reward model, and I'll tell you immediately how I do that. But it's able to just reduce it significantly in terms of the test time. In terms of the time required. So this is what we did. The autoregressive reward model arm is a reparameterization of the reward. Very simple. So what you did is rather than give the full freedom for the reward model, you train it to be a log probability. And in fact, there's a log probability over the entire trajectory. And as a result, it's just the log probability of every token trajectory based on their context before. Now, you may think that this is even more susceptible to reward hacking because I'm essentially trying to assign a reward for every token. Is that true? People think that reward hacking problem is more serious in step reward rather than the outcome reward. And I agree with that. But I don't think that actually this token level reward model is more susceptible to reward hacking just because we are restricting the function space here. We're not allowing a full freedom. We're restricting the reward model to live in the log probability space. And that is a deliberately selected space that restrict your function, with the same amount of data, it's more likely that this function is less likely to have like picked up all these artifacts and thus have reward hacking. And of course, eventually, if you still worry about reward hacking, you could use the method we previously talked about to find failure cases and catch the reward model iteratively. Okay, training of the arm is extremely easy. You might be very familiar with this equation. This is sort of like the equation of like how do you learn a reward model from preference data, right? A trajectory level preference. But you can see the training objective of arm is not that important once you've switched from the trajectory level rewards to the token level reward. Because what you're doing here is essentially just, again, the differences between the preferred and dispreferred. And then, just sum over all the tokens. Yeah. Well, the data that you need for doing this is essentially still the exact same data you use for trajectory level reward model learning. So you only need some trajectory level preference data that you collected already, which I think is really cool. Now the inference, now that you've learned the pi-r, which is the trajectory, the token level reward, you could just use it for inference directly. Pictorially, it works like this, right? Before you have to do the full completion to get the score of the RM. Now you only need to directly query from the token level reward. It's much more faster. Now, some results I want to show you, like one of the things you did is, to align with general human preference. You have a very small R model, 7B, but you're also, just steering the same sized 7B model, base model. So we did some kind of, head-to-head win rate comparison here. From this, what I highlighted basically says that it's outperforming the state-of-the-art test time alignment baselines, which is not very surprising, given that we actually published a paper on this. But I think what's very interesting is that it actually matches the test time alignment baseline, which I think is really cool, showing that you do not really have to actually train the model or DPO the model to actually make it align to some kind of reward or RL, the model. You could potentially just do a test time steering. Well, it's also very efficient, compared with all the other things. But you may still ask me, why do I want to do test time steering? I could still prefer to train the model. Essentially, I could just forever improve my model, right? But another thing I want to show you is this weak to strong guidance, which essentially says that, I can train a really, really small 7B model and potentially reuse it, even for steering models that are 70B or 700B. Is it possible? So we did some experiments. Here, we trained a 7BR model, and then we're trying to steer this 2 to 7B, 13B, and 70B model. We're trying to steer all of them. And of course, you can come up with an unfair training time baseline, which is actually train these giant models. It's not fair comparison, but we just want to see how it works, how it compares. Now, if you look at the results, what's really interesting is if you compare with all the test time alignment methods, GenR, which is the orange bar, is the best, is way better. But what's more interesting to me though is the 7BR model is able to steer the 70B model and almost reaches the performance of directly training that 70B. I think that's really cool, right? That's the fact that you're able to just do it so well with a 7B model rather than like fine-tuning a 70B model, I think it is pretty impressive here. What's even more interesting, I think, it is this multi-objective alignment where, you do not have to pre-bake anything into your base model. You could, in fact, use your base model, which is a general purpose, and steer the base model to many possibly evolving objects that can change over time or change from one user to another user. And in fact, you do it, it's like, through this kind of, summation of different arms that you care about. You could put a coefficient there, and you can even get your user feedback to fine-tune these coefficients or, like adjust the coefficients to, make the users happier. Yeah.
So are you like kind of reusing the KV caches of previous tokens to not have to do like forward pass multiple times when you're trying to compute the reward and the next token? Like how is it like actually operationalized? Because I'm guessing if you did a naive forward pass on every token, that would still be quite expensive.
I don't know whether I understand, but this is exactly what's going on. You are just doing this.
Yes, so like when you're calculating YT, given everything before,
so when you are in test time, you have to predict next token, agree?
Yes.
So that's no cost, right?
Yes.
But when you predicted that token, you just need to add that token to a score. Like do like a modification to that probability.
Yes.
Also no cost, right?
Yes.
So overall, no cost.
To get the actual reward value, like.
Oh, to learn the reward, it's here. The training loss is just here, right? So once you minimize this, you get the pi r. You just directly use pi r. I can clarify it later.
Yes.
So it's like the same model, like there's no like additional head or anything, right? Just like another objective. I guess also sort of like related.
Actually, my question was like at inference time. Like, are you trying to reuse, like, given it's the next token score, like the score for the reward for the current token? Are you like reusing the entire cache of the model so that each next
I feel like there
iteration-
is a huge misunderstanding here because it's not related to cache or anything. It is just the inference time. Next token prediction, you have a probability to sample from. I'm just saying that I wanted to make some modifications on top of that probability, adding a signal that is already pre-trained. So it's a reward signal added to the inference probability.
And so
every
every
token
model is used to
generation.
get the reward signal, right?
What is the question?
So which model is giving the reward signal? Like the 7B model?
That's the whole talk, which is the ARM, the ARM thing, the ARM model. I think maybe I didn't make it clear. Something is really misunderstood or something.
Actually, maybe one thing I just want to make sure I understand, just to be clear, that basically the cost for doing this is whatever the inference requirements are for the ARM model. So in this case, it's like a 7B model. So whatever the whatever your sort of total system inference cost.
You have to query the ARM model.
Yes. Okay. So like there's you've substantially offloaded the training cost because you don't have to do GPO on like the base model. You get this nice flexibility because you can use sort of different ensembles of ARM models, flexibly depending on your context. And basically the cost you pay is whatever the inference demand is for the ARM model, like on top of the base model, you already hit that it's guiding you. Like in the case of like almost 7B in the ARM model, like the sort of total inference cost is essentially like 14 billion parameters worth of inference.
Yeah.
And then it scales up such that like you actually get this favorable thing where you can have a model that's a fraction of the size doing the guiding. So the total inference cost is only a fraction more.
I see. Okay, I see. I understand the question now. So yeah. So I guess the difference here is like before you just look at anything here. Before you only have to do forward pass for the base model. Now you also have to do forward pass for these other models, but you could do that in parallel. So it doesn't necessarily have to increase your wall clock time, but do increase your flops.
Mm-hmm.
Yeah, that's true.
Okay, cool. I just want to make sure. Thank you for clarifying.
Yeah. Okay. Cool. Let's see. So I sort of also extended to the multimodality models, like where we say, can we also do the similar things of like steering in a step by step using a vision value model? And I think some of you are actually asking me how to do this, and I think this work could potentially give you a solution on how to steer a step by step the reasoning process and potentially give you better critique. Yeah, so this is also another way of doing things. I'm gonna keep it because I feel like I'm running out of time.
Still have about 20 minutes.
We'll still have 20 minutes. I have a lot of things to cover. More interesting thing, this extension to multimodality is actually, I think it is really a repetitive of what I already have talked about. So let's look at this. I think this is actually very interesting that, we explained how, jailbreaks or how do you make the model safe and how do you do that during test time, right? How do you steer it during early stages? And, people have been trying to come up with solutions by actually calibrating the language model's output distribution or refining the safety prompt iteratively for defenses. But none of them actually really work reliably. One of the things we realized the way to do it is potentially just doing the controlled decoding we just talked about, where you have the base models lodges out there, and if you kind of steer the lodges towards the safety score, if you do have a safety model, then together they could give you a much better aligned score that you can sample your next token from. And as a result, we proposed this immune method that is able to defend pretty reliably against these jailbreak attacks. Now, I think this is even more interesting when you think about the reasoning models. A reasoning model may become better at reasoning, but less safe, as we talked about. And how do we deal with that? Effectively, we could also deal with it using kind of early steering. So the way to do it is very simple. Let's say you have an adversarial query and the reasoning model is starting to reason based on this adversarial query. Of course, at the end of the day, you really hope that the model doesn't, get tricked by these adversarial queries. But during every thinking step, right, step 1, 2, 3, 4, you could potentially employ a safety model to evaluate whether the step is good or not. And this safety model could potentially be like a step level safety model or just an overall outcome safety model. And if the model somehow decided this is below the safety threshold, then you could do some early intervention. The way that you can do it is literally just inject in your training trajectory something like wait, think safely. So just that 3 words, you inject into your training trajectory, your reasoning trajectory, and then you just let the model decide what to do next. In fact, what we find really surprising is that if you just do that in the early steps, then the model will become much, much safer than just not doing that. And it didn't do much, actually. You could potentially do that essentially for every step, but you don't want to waste the model's kind of, token budget, right? So you only do that when you feel like the safety is a concern during that step based on the safety model. And this early steering really takes you to something really, really much safer. So as a result, you can see this safe think is able to, defend against these jailbreak tasks. So trust must be maintained during reasoning, not audited only after generation is kind of the message I want to say here. Now, once we've learned how to do the actuator or how to design the intervention to keep the model more trustworthy, now I also wanted to finally come back to the concept of self-improvement, right? So how do we amplify those capabilities? So before we said the models can potentially be guided by a reward model, or be distilled from a stronger model or guided from a stronger model. But these are all external informations. When your models become the strongest, then there is a possibility that none of the external information is useful to you anymore. None of the human knowledge is useful to you not anymore because you've already learned all these human knowledge. It's also possible that none of the data is useful to you anymore because you've used all the data in the world. So what can you do to actually, self-improve, or is it even possible to have a self-improvement here? The real question is to think about the dynamics between data and model. Like whenever you're thinking about a model, you cannot get away from the data that's training the model, right? So even for self-improvement, I guess the real question we wanted to ask is, where is the data coming from? Is it always the better? The more the better, or do you care about the data quality? If you do care about the data quality, what is a good metric for data quality? Can you actually potentially self-generate data so that you can, generate data that do not cause your model to collapse and essentially do improvement? Is it possible? I guess the first question I wanted to talk about is always the case that more data is better? I think this could be related to what you guys are doing here. I'm sure you agree with me that data quantity is good, like scaling quantity is good, but still it yields some diminishing returns. You're seeing smaller and smaller effects of the data scaling. But data quality is actually also very important. So in this work, what we end up doing is to come up with an answer to what is a good quality data for a model. We used to think that human difficulty is a good proxy, but it ended up being very unfortunately not true, because human difficulty is not model difficulty. We see a lot of situations where humans think it's easy, model think it's hard, and human think it's hard, and model could think it is easy. So we really want an effective learning to, this requires model-aware quality metrics. Now, the Monte Carlo tree-based sample selection is the solution here. It is just a Monte Carlo tree iteration of expanding the tree to try to solve a problem. But the kind of proxy we use here is the iteration. So how many iterations you need to solve the problem becomes the difficulty level. So this is how we do it. Let's say you have a question and you generate answers based on some model. You do some Monte Carlo tree of expansion, like search every step and change the step to a different step, expand and so on. And for iterations, you get some answer. And if the answer is not correct, you're gonna continue the search until you find the right answer. So you can see the iteration number goes up, and you just keep going and keep going until you get the right answer here. So let's say for this question, when it's iteration number 6, you get the right answer. Then you go through a threshold and say, hey, this is greater than 5, I'm gonna maintain it and put it in my replay buffer. But if for another question, the iteration number is only 3, then you just discard it. And that simple kind of filtering process actually made a huge difference here. So we started with 70B model, 70B 70K training data. And then, through this filtering process, you end up just getting 11K samples for training like a 7B model and 7.5K samples for training a 72B model. So just using those samples, we use an RL fine tuning, and we got this think-alike VL family, both for 7B and 72B. You can see the results. I think it is pretty impressive. On the x-axis, you can see the model size. Y-axis is the accuracy in the MathVista benchmark. So you see reasoning models here, base models here, and the performance is sort of Quinn models, 32B, 72B are good. But see, our 7B model is actually achieving almost state-of-the-art. So small size, even compared with 72B models, is comparable results. So this is where we have. But if you look at our 72B model, it's even way better than any state-of-the-art result. But what's more interesting, if you think about the data we use for training these models, post-training these models, one is 7.5K and the other is 11K, right? Way smaller than any of these other models out there, and also not distilled from anything. It is just self-improvement.
Are you just doing one epoch on the data, or are you?
That's the only.
So this is also reduced post-training compute as well.
Yeah, that's true.
You're not repeating the data more to compute now.
Yeah. So this basically means that smartly using the data is way more important, just like brute forcefully dumping everything into the data for training. So yeah, as you can see, that consistently show advantage across both scales for 7B and 72B. Now, I guess we've really come up with a new design principle that the trustworthy system should be trained not only on more data, but also on failures, uncertainties, and the smarter ways of using data. So the final question is, how do you do self-generated data, right? So if you are able to train like a self-critic eventually for self-improvement. So in-context self-critic was kind of the solution. We tried something really interesting, like, by just refining your prompt, but providing a more detailed rubrics. So if you have a more detailed rubrics, you could potentially give more guidance for the model to do critic. And just that made a huge difference in terms of the self-critic capabilities. So indeed, another example showing prompt engineering is pretty useful and pretty important for you to pick out the right information out of like the large amount of information that it generates. We also tried to use this for doing self-improvement. In fact, self-improvement was quite interesting here that once you're able to get the positive and the negative responses, you could potentially use it for for better go back and improve your model, right? So with the positive and the negative responses, you could just like using DPO or these other alignment methods or RL methods to go back to make the model better. And you can see the results are pretty impressive. Like, this kind of everything just from the model itself, no external information whatsoever, just the kind of like improving the critic capability, you are able to just be much better than your baselines. So test time, you could also do guidance with this self-critic capability. Now you're able to critic better. You can generate a lot of responses as candidates and then choose the one that is best, right? This will also improve your overall capability as a result. So you can see more of that. In fact, I think Quinn 3 VL models was using the same concept as what we did. We're using DPO to make the model better back in 2024. But Quinn 3 VL used GRPO, the same concept of in-context self-critic, but they were able to make very good models using that and GRPO. Okay, so finally, I think a lot of people are finally in the debate of like, can generative AI really truly self-improve? Some may say, you cannot generate anything from nothing because there's, no new information, no gain, first principles of thermodynamics. But others may think, yeah, as humans, we're able to self-improve because we're able to seek out new information, seek out new material, and go out there to understand the unknowns and explore the world just beyond our current capability. So this gives us like a question of what if we can actually find the right question, generated on demand. So as if you have an infinite data supply, and this infinite data supply is tailored specifically to what your model is struggling right now. Is it possible? And as a first step of like exploring that, we did this project called Morse 500, which is an infinite data playground. Essentially, you can generate infinite amount of data. And well, by infinite, I'm exaggerating a little because we have question templates. So we come up with a few question templates, and you're able to modify the difficulty level of this kind of questions based on the question templates. But what's more interesting is all these kind of reasoning things are essentially reverse engineered. So we come up with a template, but we first come up with the answer and then reverse back to the question. And as a result, you can guarantee the answer is correct and also the reasoning trace is correct. So this is the first, the first ever, because people usually collect data by having people annotating the reasoning trace, but this reverse engineering actually made it possible to guarantee the reasoning trace is correct and the answer is correct. Because we start with the answer and then go back to design the question. So I think that's a really smart way of doing things. Ended up like getting really, really difficult questions generated, as you can see. In fact, I think many of them are really hard. I struggle a lot answering those questions. Abstract reasoning, spatial reasoning, temporal reasoning, so on, planning, physics reasoning. If you look at the humans, humans still pretty much struggle with these tasks. But existing models are even worse. We haven't tested the most recent models like 505 or something. I'd be curious of testing those on this benchmark. But yeah, so finally, I just want to say trustworthy foundation models about building models that can actually detect, explain and recover. It shouldn't be a static mindset. It should be a dynamic mindset. We should learn from failure. We should self-improve. And sometimes we just need to steer things at early stages, maybe at the reasoning stages, to make things much more trustworthy. Thank you. That's all.
Yeah, I was curious about the steering. So, first of all, I think it's very impressive that you're able to like get the reward model to be stable because I think often when you're dealing with log problems, that can be very difficult. But I was curious, like just at a higher level, like how important do you think steering is for this framework? Because I feel like steering is usually like a post hoc adjustment. So do you think like the next step is to try and do some sort of RL to get the model to like
I think
internalize that
steering,
steering?
yeah, I think steering is very important in the sense that, you really wanted to find the needle in the haystack, right? You generate a model, generates a lot, and you want to find the one that actually is the right thing or the good thing. And how do you do that? Sometimes you couldn't even generate high quality data. If you're able to steer your model to generate better data, then you're more likely to find better gold and then use that gold to further improve your model.
Yeah. Then I was also curious, when you were creating the RM, I think you worked off of like the DPO law. So one of the our previous speakers in book, he worked on a paper called value augmented sampling, which was doing a similar thing, but with the PPO loss instead. So I was curious, like whether one of those losses, like why you paying for the PPO out of like the different
because it's a random choice. I don't think it was a deliberate choice.
Okay.
Yeah, I would definitely not do any DPO right now if I can do RL.
Okay.
So in the method where you were sampling based on the number of MCTS iterations, I was wondering like if you feel there could be an order in which you sample those prompts. Like I guess you chose k equal to 5 as a strict threshold. But would like varying the difficulty or the k count with time also be an interesting strategy there?
MCTS works in a way that's where you expand matters. So, you only expand at a place that's more likely to lead you to the right answer.
Yeah.
So that's why it's naturally already baked into, the iteration number. So only iteration number matters because, it's already a reflection of the most likely answer. So if your model is most likely to generate something, then you are likely to have already found it in the early iterations.
Yeah, so I guess my question was like, do you think that we could use like a curriculum where you sample the examples which took more MCTS iterations later on when you're doing RFT?
Yeah, exactly. Yeah, that's a very good point. So we did something really, really dumb, but also that dumb thing was after some kind of ablation. So we only did like very simple things of like just thresholding, right? But you could imagine like you could design more sophisticated curriculum. But for this specific model building, we didn't find the curriculum to be very useful. Only the filtering is very useful. It's getting the best result.
Got it.
Yeah, which we definitely tried, but unfortunately, I think either we didn't try a very good sophisticated curriculum design, or the curriculum ones that we tried are not really helpful, comparable. Not, it's like if you don't have it, it doesn't hurt you.
Yeah, because the iteration count looks like a nice proxy for the difficulty. So I was curious if that's
Yes, we actually tried to explore that quite a lot, but yeah, thanks.
Yeah, this might be a very simple question to answer, but like on this slide, I noticed that there are some categories that are like multi-choice, whereas open-ended. Initially, I was starting to realize like, okay, maybe the multiple choice ones would be a bit easier to solve. That's why there are fewer samples there. But then I quickly changed my mind after looking at natural image understanding. So do you think there might be some bias to having multiple choice questions in your prompt or what you're trying to solve that could make it a bit easier to get to the right answer faster or use less iterations? Or
So the reason
is there an indication of difficulty based on the formatting of your question as opposed to the theme of the question itself?
Well, I think you're right, but at the end of the day, when you are using multi-color tree search to search for it, you still have to come up with the reasoning process, right? So you could just randomly guess something, right, out of all the choices, but you still have to reason. You have to think about the thinking process and then come up with the final answer. So in some sense, the way that you're using multi-color tree search is already accommodating both the open-ended and the multiple choices.
Okay.
In my opinion,
Mhm.
right? So also, to verify the result, it's probably going to be a little bit better if you could make everything into like a specific format and to verify whether you got the right answer or not. Yeah.
I guess I also have a quick question in this process. Wondering like how much compute did you use for like tree search compared to like the say the actual training?
A lot of
A lot of
computing.
compute.
The good thing is it's one-time cost.
Hmm.
There's a lot of compute. So actually, I think what's interesting is come up with more efficient metrics.
To search.
Right, looks like we also at time.
Yeah,
Again, once
thank
again,
you.
thank
Thank you so
for
much.
sharing.